Okay, so welcome to the final section, 8.3 of this chapter. And what we're looking at now is our third or fourth, if you count circles and ellipses separately, type of conic section. So what did we talk about before? We talked about parabolas, which had our y minus k times 4p equals x minus h squared. We talked about ellipses, which is our y minus k squared over b squared plus x minus h squared over a squared. I know I wrote that in a weird order, sorry. And if a equals b, then this is a circle. And now our third type of conic section is hyperbolas. Okay, so hyperbolas are very, very similar to ellipses, except that the foci are on the outside of the vertices. So remember, for an ellipse, you had a center, two foci, two vertices, and the ellipse goes around the foci through the vertices. Well, for a hyperbola, again, you have a center and foci and vertices, but this time the vertices are within the foci. So the shape goes through the vertices, still around the foci, but now it's facing outward, and this shape is called a hyperbola. So that box that we used to draw our ellipses, we can still use it now, but instead of drawing like an oval inside of the box, which is how we did our ellipse, now what we're doing is we're using that box to draw asymptotes through the corners of the box so that we can draw our hyperbola on the outside of the box. Okay, so how is this different than an ellipse? Well, it faces the opposite direction. Instead of coming in together to make an ellipse, now they're facing outward to make a hyperbola. And the difference of how we can tell them by the equation is that subtraction sign. So now we're looking at what happens if I subtract the terms instead of adding them, and that is how we get a hyperbola. So the key things to look for to tell these equations apart: a parabola, only one of the variables is squared. An ellipse, they're both squared and added together. A hyperbola, they are both squared but subtracted. And we can see when the y is subtracted from the x, or we can see when the x is subtracted from the y. So the hyperbola is defined as the set of all points in the plane whose distance from two fixed points, or the foci, have a common difference. Not a sum now, but a difference. The line through the foci is called the focal axis. So just like on an ellipse, the line that went through the foci was called our major axis. Now the line through the foci is called the focal axis. So let's fill in some information in this table here. Our standard equation, we have two again. So we have the case where we have x minus h squared over a squared and y minus k squared over b squared equals 1. But different from the ellipse, we had a plus here. Now for the hyperbola, we have a minus. Our second case is if the x and y switch roles. So now we have y minus k squared over a squared minus x minus h squared over b squared. So notice now we don't have that relationship that a is the biggest. It doesn't matter which one is bigger, so much so as the subtraction. Okay, so a being bigger will change whether our hyperbola is wide like this or skinny, okay? But what determines whether it's opening upward or downward is which variable goes first. So our focal axis, in this hyperbola, the x comes first, so we know our focal axis is in the x direction. So we have the equation of a line that's going across is a y equals k. So x came first, so that means that our hyperbola is opening in the x direction, means it opens sideways. Okay, so then the focal axis goes through the vertices and the foci, meaning it looks like the x-axis, which has an equation y equals, and then if it's going through the center still is hk, so y equals k. For our second column, we have y first, so our hyperbola is opening upward and downward, which means the focal axis goes up like the y-axis with an equation of x equals h. The foci are still a distance c away from our center. So we have here for a horizontal hyperbola, h plus or minus c comma k. And then for a vertical hyperbola, they have still a distance c, but now it's in the y direction. So that's h comma k plus or minus c. Again, two foci. So we're using both the plus and minus. We should get two solutions. Vertices, those are the points that are on my hyperbola, just like they were on the ellipse. And that's still a distance that we call a. So h plus or minus a comma k. And h comma k plus or minus a. These should look very familiar because they're very, very similar to the same formulas that we use for an ellipse. The only difference is that in our standard equation, we have subtraction. And that does have effects throughout, but the foci and the vertices have the same formulas. Now, instead of calling this a major axis, we call it a semi-transverse. So instead of semi-major, semi-transverse. This is the big one. This is the one that goes through in the direction of the focal axis. So again, our semi-transverse axis has a length of a, which means semi-conjugate, which is what we would have called before the minor axis, has a length of b. So it has kind of the same meaning as the major and minor axes for an ellipse, but because there's not a distance across a hyperbola keeps going out to infinity in all directions, and therefore there's not a distance across a hyperbola. So we don't call it the major and minor axes anymore. Now we're calling it those distances, and it's the same distances that we used to make the box, just like we did for an ellipse, same distances that we used to make that box for a hyperbola. Okay, so the Pythagorean relation. Now for an ellipse, we said that a squared equaled b squared plus c squared. But notice now, and I'll draw another ellipse here, or another hyperbola here, the center, so my distance c goes all the way out to the focus. My distance a is inside, so a is now smaller than c. A is not the biggest anymore. And b is the distance from the center out to, so this is b. Okay, so when I draw my box, the distance b is perpendicular to the focal axis. The distance a is along the focal axis, but c is my biggest value. So we end up with the Pythagorean relation c squared equals a squared plus b squared, which is the same as the Pythagorean theorem. C squared equals a squared plus b squared. Okay, so for a hyperbola, a different length is the longest because the focus is outside of the vertex. So a is not the biggest anymore, c is the biggest, and so we end up with this Pythagorean relation. And finally, our asymptotes, these lines that we drew, if you look back at the sketch, notice the slope here is b over a, okay? If it was turned the other way, it would be a over b. So if you solve the implicit form of the standard equation, you end up with your asymptotes at y equals plus or minus b over a. There are two asymptotes, so we solved for both of them, times x minus h plus k. So the slope of the asymptotes, and this is the thing that we'll use the most, the slope of the asymptotes is b over a, right? It's the second denominator over the first denominator. or the y denominator over x. Rise over run, right? For our vertical hyperbola, we can do the same thing. We solve for the slope, and this time plus or minus a over b times the quantity of x minus h plus k. Notice again, we have now my denominators, it'd be first over second, or you can look at it as the denominator under the y, which would be the rise, denominator under the x, which is the run. So rise over run. Okay, so that's the key to remembering how to find the slope of your asymptotes. Rise over run, rise over run. Same as slope before. Okay, so let's do some practice problems and apply these formulas. Example 1. Find the vertices and foci of the hyperbola 4x squared minus 9y squared equals 36. So the first thing to do here, remember, just like for ellipses, our hyperbola formula says equals 1, so we need to divide everything by 36. So we have x squared over 9 minus y squared over 4 equals 1. So that means that A is 3 and B is 2. Okay, now this is not because 9 was bigger than 4, but just in our context, in the standard equation, A always came first. Does it really matter if you change the order of A and B? The only reason that it would change is that all of the values that we put in our formulas for A and B might switch if you switched the order for A and B. So maybe put a note to yourself here, A is first, whereas for ellipses, we can go back and label that for ellipses, A is biggest, or bigger, because there's only 2 values, right? So that's another way that we can keep track of the difference between ellipses and hyperbolas. Okay, so we found A and B. We want to find the vertices and the foci, so we need H, K, A, B, and C. So first we need to find H and K. Well, looking at this, nothing is subtracted from X or Y, so HK is 0, 0. So we can say the center is 0, 0. And then we say, okay, well, let's find the vertices first. Vertices are the value of A. So I need to know which way is this going, left, or is it going sideways or up and down? X is first, so this is going sideways. Centered at 0, 0. My vertex is a distance of A away. So that's 3. Now this would be minus 3 and this would be plus 3 along the X values. So we have plus or minus 3 comma 0. And then we have the foci. Foci are a distance of C away in both directions. So that would be like a minus A and a plus A, minus C and plus C. Again, it's in the X direction. So now we have plus or minus whatever the value of C is, and we don't know the value of C. So how do we find the value of C? Well, we use our Pythagorean relation, and we say that C squared equals A squared, which is 9, plus B squared, which is 4. So C squared is 13. So C is the square root of 13, and that's what goes here. So we have the center vertices and the foci, but we didn't really need the center, so I'll leave it out of the box. Let's take a look at the next page. Example 2, we want to find the equation of the hyperbola with the given foci here, whose conjugate axis has a length of 4. Conjugate, remember, is our smaller one. So how I remember this is trans, like transatlantic, or trans-Pacific means across. So the semi-transverse axis, or the transverse axis, goes across the 2 halves of the hyperbola. So I think transverse is across. So when I look at the hyperbola, the one that goes across the halves is the transverse. and the ones that go between is the conjugate. Okay, so that's kind of a trick that I use to remember it. Trans is across, and the transverse goes across the two halves. So the conjugate axis, the shorter one, or the perpendicular one rather, has a length of 4. Okay, so that means that the semi-conjugate axis will be 4 over 2, which is 2, and that's our value for B. The distance between the foci has to be exactly twice as much as the distance from the center to a focus. Another way of saying that is the center has to be halfway between the foci. So if I look at these points, 0, -3, and 0, 3, exactly halfway between them is 0, 0, giving me a distance of 3. Okay, I'm going to go ahead and sketch this so that I can see what's happening so that we can then find the equation. So we said the foci are at 0, -3. Remember, the foci are not on the hyperbola. They're inside of the hyperbola. So my hyperbola is going to go around the foci. Here is my center. My semi-conjugate axis was 4, so that's 2 this way and 2 this way. Okay, so I have parts of my box, but I don't know the other side of my box. I need to find A. So we say c squared equals b squared plus a squared, which means that a squared is c squared minus b squared. A squared is 9 minus 4. A squared is 5, so a is the square root of 5. The square root of 5, if we double check it, square root of 5 is 2.2-ish, 2 1/4. So it's going to be somewhere like this. There's my vertex, and there's my vertex. Obviously not a perfect drawing, but it gives us an idea of what all of our values are and how to create our equation. This is an up and down hyperbola, so that means y is going first, minus k. Well, if my center was 0, 0, so then h is 0 and k is 0. So that's just y squared minus x squared. You don't need the parentheses, but I like to put them to remind myself that I already checked for h and k. Divided by a, always goes first, a squared and b squared equals 1. And then we simplify. So y squared over 5 minus x squared over 4 equals 1. And remember, for hyperbolas, a could be smaller than b. In this one it isn't, but it could be. So we could have switched the 5 and 4, and it would still be a and b, because a is always first in a hyperbola. Let's take a look at example 3. Find the standard form of the equation for the hyperbola whose transverse axis has endpoints -2, 1 and 8, 1, and whose conjugate axis has a length of 8. So I know both of my axes, right? So the transverse axis, this is like the major, and the conjugate is like the minor. So let's go ahead and plot some of these points. So we've got -2, 1 and 8, 1. And that means my hyperbola is opening sideways because that's the transverse axis, the axis that cuts through both hyperbolas. Okay, so I know that these endpoints are also called the vertices, whose conjugate axis has a length of 8, which means the semi-conjugate 8 over 2, 4 is B. Okay, now my center has to be exactly halfway between these points. So if we count, they're 10 units apart. 8 and 2 is 10 units apart. So the center has to be 5 units apart. 1, 2, 3, 4, 5. So my center is at 3, 1. So H is 3, K is 1. A, which we just counted, is 5. We found that B is 4. Okay, now we're looking for the standard form of the equation, and again, we can find C, but we don't need to because C is not part of our standard form equation. If we were to draw this hyperbola, it would be something like this. So we have sideways x is first, x minus h squared over a squared. I'm writing out the formula over b squared equals 1. So now we have x minus 3 squared divided by 5 squared is 25 minus y minus k squared over b squared is 16 equals 1. All right, let's take a look at example 4. Find the center, vertices, and foci of the given hyperbola. Okay, now I want you to pause and think for a second, which one is A and which one is B? In a hyperbola, A always comes first. So A is 3 and B is 7. H is -2, K is 5. So I'm going to write them over here. H is -2, K is 5, A is 3, B is 7. X is first, so we know this is a sideways opening hyperbola. The center is at -2, 5. This is a distance of 3 away to each vertex. And then we don't know C, so we don't know how far away to the foci. So we need to find C. C squared is A squared plus B squared. C squared is 9 plus 49, which is 58. So C is the square root of 58. So then we could say the distance here to here is the square root of 58. Again, let's check how far that is. Square root of 58 is about 7.6. About 7.6. So that means the distance here is going to be 1, 2, 3, 4 and a half. A little bit more than 1, 2, 3, 4 and a little bit more than a half. So how do I find these points? Well, let's start with the center we have already found is -2, 5 from HK. The vertices, those are the ones that are on the hyperbola, are -2. They change the x value, plus or minus 3, my a value. I went to the 3 to the right and 3 to the left, which is -2, whoops, not -2. -5, 5, and 1, 5. And then the foci. The foci are the square root of 58 units to the right and to the left. -2 plus or minus the square root of 58, 5. I can't simplify that even if I split it up. So there's my answers. The center, the vertices, and the foci. And then we're done. Notice how I go back and I reread the instructions to make sure I've answered the question. It's a good practice to get into. Let's take a look at the next page. So when we were talking about ellipses, we talked about Kepler's first law of planetary motion. And since that law has been published, we have generalized, not me, but astronomers have generalized that law, that any celestial body that travels within a gravitational field of a more massive body follows a path that closely approximates a conic section. So Kepler's law said that it follows an ellipse, And now we're saying maybe not necessarily an ellipse, however, it's a conic section. Okay. So theoretically, if a comet is approaching the sun from space, it can make a partial loop around the sun and then leave the solar system. And in that case, it would follow the path of one branch of a hyperbola. Okay, so again, we're going to talk about eccentricity. And that means how far away is the focus from the center or from the vertices. So we're talking about how stretched out is this conic section. Okay, so in the last one, it looked at, it was really like how far off of a circle is the ellipse. And now we're talking about how far off of a standard hyperbola is our hyperbola. So how much has it been stretched? Okay, and now when we're talking about eccentricity, make sure that you recognize that that is not the natural base that we're talking about. Even though it's E, it's not the value of the natural base, it's a variable E. Okay, so let's look at example 5. A comet following a hyperbolic path about the sun has a perihelion distance of 90 gigameters. When the line from the comet to the sun is perpendicular to the focal axis of the orbit, the comet is 281.25 gigameters from the sun. Calculate A, B, C, and E. What are the coordinates of the center of the sun if we coordinatize space? So the hyperbola is given by that equation there. Okay, so the first thing we have to do is recall, what does perihelion mean? And I'll show you on the image so that you can remember. Perihelion is the, here we go. Perihelion is the focus or the vertex that is closest to the focus, versus the aphelion was the focus or the vertex farthest from the focus that we're asking about. Okay, so we're talking about which arm of the hyperbola is closer to the focus that we're studying. So the arm of the hyperbola closest to the sun is what this means. Arm closest to the sun. So if this is the sun, I've got two arms, we're talking about that one. Okay. The distance here is 90 gigameters. So let's draw a nicer picture. This one's kind of hard to draw on or to label. So I'll draw it underneath. Here's the arm of the hyperbola. Here's the sun. Here's our focal axis. Here would be the other arm of the hyperbola. So what role does the sun play? Well, the sun is a focus. So to find the center of the sun, we're actually asking, find the focus. Well, I know the distance here is 90. Here's my center. This distance is A. This distance is C. From our given equation, we're assuming that H is 0 and K is 0, which means that this distance, 90, equals C minus A. The difference in distances of C and A is 90. Okay, so if 90 is C minus A, then I can add A to both sides and see that C is 90 plus A. So I've solved for C, but it's still in terms of A. So I would really like to be able to find out what the value of A and B are in order to finish this equation, or to at least find the focus. We'll need to use our second piece of information to finish solving this, which is that when the line from the comet to the sun is perpendicular to the focal axis of the orbit, the comet is 281.25 gigameters from the sun. So what the heck does that mean? That means when I'm directly perpendicular from the sun, so the comet has to be perpendicular from the sun, or perpendicular to the focal axis from the sun. So the comet is here. The distance to the sun, that is this distance here, is 281.25 gigameters. Okay, well, I know that since my center was 0, 0, this point has a y value of 281.25 and an x value of not c, but we went to the left, so negative c. Which means that if I substitute x and y into my equation, I'll be at least a step closer. So we can substitute here negative c squared over a squared minus 281.25 squared over b squared equals 1. So in order to solve for a, b, and c, let's try isolating the number. In order to do that, let's clear our fractions. So in order to clear our fractions, we want to multiply everything by a squared, b squared, which is our LCD. We have to multiply it to every term. So the b squared cancels, a squared cancels. Negative c squared is actually just c squared. So we have b squared, c squared, minus a squared, and then the number squared equals a squared, b squared. Again, our goal is to isolate the number, so we get all of the variables and see if we can simplify them. So let's switch these. So we have b squared, c squared, minus a squared, b squared equals a squared times 281.25 squared. I noticed these both have a b squared that I'll factor out. Also notice there's an a squared on this side. So I have b squared times c squared minus a squared over a squared equals 281.25 squared. Okay, well, c squared minus a squared should look familiar. If you think about the Pythagorean theorem, that would equal b squared. Well, our Pythagorean relation for hyperbolas is the same as the Pythagorean theorem. So if I have b squared equals c squared minus a squared, then I can substitute that for b squared. So we have b to the fourth over a squared equals 281.25 squared, square root property. And then I'll bring it up here. So we have 281.25 equals plus or minus b squared over a, which means that plus or minus b squared equals a times 281.25. Okay, well, I'm looking at this and I say, ooh, let's just focus on the positive one for a second. And let's try to get everything in terms of a, because a lot of these have a's in them. So how do I write b in terms of a? Well, I'm going to undo the step that we just did. So we're going to say c squared minus a squared equals a times 281.25. So since we have c in terms of a, we're going to substitute 90 plus a squared minus a squared equals a times 281.25. We have a binomial squared here, so we have to FOIL it out. 8100 plus 90 and 90 is 180a plus a squared minus a squared. Hey, that makes us happy. Equals a times 281.25. So now we have 180a that we can subtract. Minus 180a to get 8,100 equals 101.25a. Divide by 101.25. And now we get that a equals 80. How nice. Okay, so if a is 80, and we know that c is 90 plus 80, remember c was the difference, so 90 plus 80 is 170. Then we can use this same formula that we've used a couple times now to find that b equals the square root of 170 minus 80. 170 squared minus 80 squared, which gives us in the calculator 150. So we've got A, B, and C. Okay, what we really needed though to find the focus is C. And from the center to get to the focus at a distance of 170, our foci are at plus or minus 170, 0. So if I ask for list one, and I don't specify either one, you can list either of these answers, positive 170 or negative 170. If, read the blueprint, it asks for, give me the positive x value, then just give 170, 0. But both of these are foci, and since I chose which side the sun got to be on, I could have rotated the picture the other way, right? So I kind of implanted the idea that the sun is on this side. It didn't say anywhere in the word problem that the arm was going off to the left or to the right. So either of these could be answers of where the sun is. Okay, I want you to think about that and then go ahead and write your summary and reflection and then type it into Edpuzzle.